In an earlier video on ionic bonds, we briefly discussed the concept of bond energy. Bond energy for a covalent molecular bond reports how much energy is needed to overcome the shared pair of electrons and separate two atoms from each other. It always takes energy to break a bond, so breaking a bond is always endothermic. And what's more, we always get energy back when we form a new bond. The process of bond formation is exothermic. With these two concepts in mind, we can consider at the most fundamental level the process of a chemical reaction or chemical transformation being one in which bonds are broken and new bonds are formed. The breaking of bonds requires energy, and the formation of new bonds releases energy. Because we can associate enthalpy changes, delta H, with either process, we can sum all of those processes together to come up with a cumulative enthalpy or delta H for a reaction as a whole. The overall enthalpy of reaction, which we will call delta H of reaction, given the symbol delta H RXN, will be a result of any bonds breaking and therefore requiring an input of energy, less any bonds forming and releasing energy. Mathematically, this same conceptual equation looks like this. In this equation, the delta H of reaction is equal to the sum of, which is what this sigma symbol means, all of the bond energies in total for every bond that breaks. We're going to subtract from that the sum of all of the bond energies for all of the new bonds that form. So what we're going to do is come up with a list of all of the bonds breaking, their associated energies, and sum all those together. A list of all the bonds forming, their associated energies, sum all those together, and subtract from the breaking the forming energies. As an example of how to implement this equation, let's calculate the overall reaction enthalpy change. For this reaction, H2 plus F2 makes 2HF. In this chemical reaction, all of the bonds that are represented by our reactants on the left side of this reaction have to break. So, all of these substances will form new chemical products. Our reactants have bonds that break. Those bonds include the bond between two hydrogen atoms in H2 and two F atoms in F2. So, we have one bond between two hydrogen atoms and one bond between two F atoms. According to the chart over at the right, the amount of energy required to break a hydrogen-hydrogen single bond is 432 kilojoules per mole. And the bond energy for a fluorine-fluorine single bond is 159 kilojoules per mole. We're going to sum all of those energies together to get a total sum of all of the bond energies for all of the bonds that are breaking in this reaction. 432 times 1 plus 159, also times 1. Added together, give us 591 kilojoules per mole of reactant. Conversely, any bond that's represented by products on the right-hand side of our reaction will form. All products in this particular reaction have bonds that have formed anew compared to the reactants. There are two HF molecules. Each one has a hydrogen-fluorine bond. Since there are two of them, and each bond has a bond energy of 565 kilojoules per mole, then the sum total of all of the bond energies forming and therefore releasing energy is equal to 1,130 kilojoules per mole of product. That's 565 times the number of bonds, 2. There are two bonds because there's a coefficient of 2, out in front of this hydrogen fluoride formula. To calculate our overall enthalpy change for our reaction, delta H for our reaction, we take the bond energies for all of the bonds breaking, subtract the bond energies for all of the bonds forming. That's 591 kilojoules per mole for all of our bonds breaking, minus 1,130 kilojoules per mole for all of our bonds forming. That leaves us with negative 539 kilojoules per mole. This is our overall enthalpy change for our reaction as a total whole. This means that this reaction releases energy in net. Since the sign of our overall enthalpy, delta H for our reaction, is negative, it's less than 0, that must mean that our reaction is exothermic. In other words, the net result of this reaction is that it releases energy as it happens.